Okay, that brings us to the second part, the cameras. And we will follow what is called the pinhole model. Now, you have to imagine if you have a box, this cube drawn on the right hand side, you have a small hole on the left. And then you have the outside world. So rays would come in and through that small hole form an image at the back of the cube. It will be reversed, but if the hole is small enough, it will be sharp. This is called the pinhole model, and the whole thing revolves around the idea that the path followed by the light from a point in space to the image point at the back here is a straight line. And all these lines go through a single point, that pinhole. Now, as a matter of fact, there were initially some attempts to do exactly that, to have a room, a darkened room, with a small hole in one of the sides, and then people would see the reflection of what happened outside. There were actually people going around with these kind of instruments to show to very rich people how interesting that all was. This kind of a student's version. So a very small kind of paper-based cube being built with a small hole on the other side, and here you see the reflection of this hallway at the back. The Paul Mans version of the castle version of pinhole camera. So, this is mathematically what this pinhole projection does. So you have a surface on the right, let's say with a point PO. And then you have the world coordinate system, X, Y, Z. And here this point, this surface on which the image projection will happen. At the origin, we're supposed to be this small hole to be present, through which all these rays of light would pass. Now, we have the coordinates of the point outside, XO, YO, ZO, and then where the corresponding projection will happen on that plane here on the left has coordinates xi, yi, and minus f. F is a distance between the image plane, the plane on which the outside world is being projected, and the origin. And equal triangles show us that these ratios are all the same. Notice the minus sign because we have different sign for F and ZO here, if you want F to be positive. But actually it's of course a negative depth. We call that the magnification or the linear magnification of this system. So, in fact, this simple setup would be the perfect camera, but unfortunately, in reality, it does not work. Here we built such a device. So we have a pattern being imaged from the left, so we have a light source and this F cut out. And then we go through a small hole, the pinhole, and there's a wall on the right hand side, and you see this very, very faint reflection there. So absolutely not what you would call an acceptable image. So there's simply not enough light going through that very tiny hole in the center. Now, of course, you could try to expand the hole, making it bigger. and get more light falling onto the wall on the right. Let's try and do that. So here we now expand the hole. You see this very faint reflection on the right-hand wall. Expand the hole will let through more light, so the right-hand side will get brighter, as you can see. But unfortunately, not much of the F is left. Now we get rays from all kinds of directions going through that hole and not building a good light. So what one does is to put in a lens. And the lens makes sure that points coming from the same point in space, again, are all redirected onto the same point on the back wall. So a lens is what makes sure that we have enough light and a sharp image. But there is a price to pay, as we will see. So here is the equation for that lens. You see light now coming from the point PO, different rates, reflected from PO, in different directions on the right here, all falling onto the lens. And then the lens makes sure that all the light coming from PO is redirected to hit this image plane onto the same point PI, according to the equation that you see on the left. This is a thin lens equation. And F is actually a parameter following from the lens. You can also see that if you fix F and you fix the distance of the point PO with respect to that lens here, where also the origin resides, that is only 1 ZI, matching that formula. And this is the price I was talking about. So unfortunately, by using a lens, you get bright images, but they are only sharp for a certain distance. So if you are taking images, only objects at a certain distance from your camera are sharp, and all the rest is blurred. So that's the balancing act here. You can't have a real pinhole, a very small hole that will have a sharp image for all points at all distances from the camera and have enough light. You have to bring in a lens to have enough light because you want to open up the pinhole, and that then brings in this restriction. Now you only have sharp images at a certain distance according to that formula. It's called a thin lens formula for good reasons. So actually the whole equation only holds with spherical lenses on both sides. So you assume that the lens is spherical for both sides. And you also assume that the light is incoming more or less parallel to that optical axis, the horizontal axis that you see there. You also assume the lens is thin, so it's rather, the radii are not too small so that you would have kind of a sphere. No, it has to be a thin lens, then that formula will work. And you will also assume that you have the same refractive index, basically the same material on both sides of the lens. So then this formula holds. So I was mentioning before that the price we have to pay by introducing a lens is that now we only have sharp images for objects at a certain distance from the camera, from the lens. Now we have to imagine we have in fact reverted the graphic. So the outside world is now on the left. So we have our point PO in the world now on the left. This is a lens with an aperture D, an opening, under which all the light can come in. And then we have this image plane here on the right. According to the thin lens equation, we only get a sharp image once we choose a certain distance between the image plane and the lens for a very particular distance of the points with respect to the camera. Now, in reality, we can relax a bit this condition. So, in reality, of course, we have an image sensor. It consists of certain picture elements, pixels. They have a finite size. As long as we get a blob on the image plane, not bigger than the pixel, we can say that's sharp enough. And that's also what you see here. So if we go a bit too far with our point, let's say to PO plus or PO, and you follow the projection rays here, you see not a single point will be formed on the image plane, but actually a blob. But if we have a blob not bigger than B, the size of a pixel, for instance, we can say, okay, that's sharp enough for us. Same happens if you don't go far enough with your point PO. If your point PO is a bit too close to the camera, so at position PO minus, for instance. Again, in that case, you don't get a single point here, you rather get a blob. So the question now is, how much further or closer can you go in order not to go beyond this critical value B that you somehow have to define? And we won't go into details of that. You see again those rays highlighted that happen if you go too far or too close. In both cases you don't get a single point, but the rays coming from the point in the world now form a blob. In fact, there's a single point here in between the lens and the image plane, or even behind the image plane, like in this case. So what you can do at maximum motion is this. So this formula shows actually how far you can come closer to the camera before you hit that critical size B. So delta ZO minus is how much you can come closer to the camera before the image of your point will become this blob of size B. And what you see is a numerator which contains ZO squared and a denominator which only has the first degree of ZO. So the farther things are, the larger the distance become. We call it the depth of field. So if things are further away from your camera, you can have a larger depth of field. Also, notice that if you would decrease D, the diaphragm size, so if you decrease it, you get closer and closer to a pinhole model again. The more sharpness you get, the bigger this depth of field becomes as well. Now, this is only one of two formulas. So this formula answers the question, how much closer can you come before hitting that critical size B? But there's another similar formula on how much further you can go away before hitting B. And it's actually basically the same. So this formula, how much further or how much closer you can get, the depth of field is related to the different parameters like this. So if you have enough light, you can maybe rather get the smaller diaphragm and have more sharpness. But of course there will be limitations because we introduce the lens to make sure that we capture enough light. So you can't smaller or reduce the diaphragm size without having to worry about the necessary level of illumination coming in. So we have a cycle balance between incoming light, T, and a large depth of field. So, in fact, we have this similar expression here, as I mentioned, if you want to move further away. Okay. Now, the lens equation that we just saw is an idealization of what happens in reality. So you have all kinds of deviations from the ideal lens and its behavior. So we make some assumptions here. Namely, all rays from a point hitting the lens are focused onto one image point, according to that lens formula. In reality, that's not completely true. Secondly, we also assume that all the sharp images of points in space there also fall into a single plane. Also, that is not completely true. And we also assume that the magnification that we saw is the same across that image plane. Again, something that is not completely true. So there are all kinds of deviations from these basic rules, which we call aberrations. So deviations from the ideal. In fact, there are two types. One are the geometrical ones. Those correspond to deviations from the rules that we saw on the previous slide. And then there are chromatic ones. For the first ones, the geometrical ones, a good rule of thumb is that try to fall onto the lens under a perpendicular angle. It's a bad idea to have light coming in very sharply under a grazing angle onto the lens. That will create all kinds of problems. So try to fall onto the lens right in front. So paraxial rays, as they are called, are the best, generate the least problems. Now, as to the chromatic effects, well, there is a hard problem here, and that comes from Snell's law. So when we were talking about the interaction between objects, material, and light, we have been mentioning this effect. So a lens works on the principle of refraction. And unfortunately, if a ray hits a surface and then moves beyond that surface, the direction followed by the ray will be dependent on the wavelength. So if you have white light coming into a lens, that refraction that happens on the surface between the outside world and the lens will have the transmitted ray actually going in different directions depending on wavelength. And then, as things would not be bad enough, of course you also have to exit the lens, and that is again a transition between lens material and outside material. So again, refraction happening, and again, wavelength dependent angles. So Snell's law has it that depending on the wavelength, our ray, even if all the light comes in together onto a lens, will follow different directions after the lens. The question what we can do about that? Well, basically nothing much, because it's a hard law of nature. It's a price that we have to pay for using refraction as the basic methodology for image formation. We introduce lenses, with lenses comes refraction, and with refraction comes Snell's law. So there are all kinds of aberrations, so we won't dwell too much on them. Here are a number of the most often mentioned ones. We have spherical aberration, astigmatism, radial distortion, coma. These are all geometrical aberrations. And by the way, radial distortion is the one to worry most about, and it's one that we can correct to some degree with software. So that's good. First, spherical aberration. What does this refer to? Well, the problem is that rays parallel to the axis do not converge. So depending on how close you are to that optical axis, the point of convergence will actually differ. Here's what I mean. So if you have these rays rather far from the central optical axis, these rays will give a point of convergence here where you have the red point. But now if we move the rays closer to the axis, the optical axis, what happens is this: the point moves out. If we move even closer, the same happens again, still now further away. So we see that all these rays that are in principle meant to generate an image at the very same point on the other side of the lens, they don't. Well, spherical aberration, not much we can do about it. It depends on having better shaped lenses, more expensive lenses, that will typically mean. Radial distortion, which are introduced as the most common of these geometric deformations or aberrations. Here you have the effect. The center image would be the way you would want it to be. And you see that things that are supposed to be straight are straight in that image. But then, radial distortion will have an effect that curves things that are supposed to be straight. So on the left-hand side, you see all those straight lines being curved in the form of a barrel, as you can see. Or you can also have this form of deformation, which is called pincushion radial distortion. You see again, things that are supposed to be straight are now curved, but just in the other direction. You can use software to compensate for this though. If you know what is supposed to be straight in the scene, you can start to measure the deviation from that straightness and put it into a formula. So, if you have a distance from the center of projection, you can try to move these points away. And the idea is the following. So you have the optical center of your image. You have rays through that optical center, like those. And then you can move points. This is the optical center. This would be the position of a point in your original image, having the radial distortion, and then you can move that point out. Depending on the type of radial distortion, barrel or pincushion. For a barrel distortion, you would like to move points inward. For pincushion, you want to move point outward. But anyway, the distance d by which you have to move would be along the same ray. So you would move, for instance, this point out by that distance, d, and it's calculated depending on the position of your point with respect to the center of projection. This distance would be called r. And so you have to, in fact, optimize the different parameters, kappa 1, kappa 2, and so on, to get that distance correct. Notice that all the distances are positive or the opposite sides. So if you know structures that are to be straight in your image, you can measure these compensations on the basis of training images. Then you know kappa 1, kappa 2, and so on, and then you can apply that optimal correction D on all further images that you capture, thus correcting for radial distortion. You see an example of that. So that would be the original image. There's some radial distortion in it, and here you see the same image but now with radial distortion corrected for. So this is something you can do on the basis of software. You can compensate for radial distortion, and many cameras will come with some form of it. So before you start to do very metrical things where precision matters, it's often important to care about the correction of radial distortion first. Then chromatic aberration. Well, again, something we can't do much about once we have fixed the choice of our lens. But what people try to do is to achieve some form of so-called achromatization. And that means that you combine different materials into a lens. So most lenses, certainly the more expensive ones, are actually composed. They contain multiple components, often produced from different optical materials. And what people try to do is to get the same focal point here, the same point of intersection for different wavelengths. So if you have the spectrum that you can see, the visual spectrum, you take two wavelengths in there, of which you ensure through the combination of these different lens forms and materials that they behave in the same way, generate the same focal point, you know that in between things will not get too bad either. So the bottom line is composed lenses will be able to reduce the problem of chromatic aberration. We'll never get completely rid of it, it's impossible, but okay. You can mitigate the influence. Now, if you look at modern cameras, there are actually two types. One are so-called CCDs, and the other are CMOS cameras. Now, things have been moving very quickly over the last years. So 10 years ago, I should have told you CCDs are the dominant type if you have a bit better quality, and CMOS is for cheaper cameras. By now, CMOS are absolutely dominant, and CCD cameras are becoming rare. Here are the two compared. So a CCD camera basically consists of a number of shift registers. You see the blue areas, they are the light sensitive areas. So photons are being collected, and after that time, the different charges are being moved down to a readout register. From there, all the information goes out. CMOS cameras have a lot more logic in between the light sensitive areas, again in blue. You see they are smaller in comparison. And they behave more like a memory. So in principle you can read out even individual cells, individual pixels if you would like to, although that is not done in the vast majority of CMOS cameras. So they have a bit of a different technology behind them. The big advantage for a long time of CCD cameras has been the bigger light sensitive areas, the better efficiency in capturing photons, therefore getting better quality images. Here we'll see how that CCD camera operates. So you have all these different pixels, light sensitive areas in which photons are being collected. So here you have a light sensitive area, you integrate photons, and then after the integration time, information is moved into shift registers, the black areas, that are actually shielded off from incoming light. And then that information goes in another shift register at the bottom and is being read out. That's the way these interline CCD cameras operated. Okay, so an advantage of those cameras was that certainly the light sensitive area could be made a lot bigger than in the case of CMOS cameras. Now, as far as CMOS went, basically very similar technology in terms of the photon capturing, but there's an amplifier coming, so a lot of logic coming with every single pixel. And that led to all the logic that you saw in between these different pixels, thus reducing the light sensitive area. So we have lower sensitivity to light. Now the big advantage of CMOS cameras is that you can use the normal type of technology you would also use for instance, producing CPU technology. Okay, so that also means you can mix the two. You can mix logic and photon capture. So you can build these so-called smart pixels, where a lot of the computation already happens next to the pixel itself. As I said before, CMOS are by now absolutely dominant in terms of technology, because the problem of lesser light sensitivity, therefore more noise, could be reduced more and more as time went. So people have been working very hard to improve the quality of CMOS images to become close to the quality of CCD. And for instance, in your mobile phone, you have typically a CMOS camera. So by now, the number of CMOS cameras around is huge. Okay. Here you see, in fact, how different resolutions are starting to pop up. So initially, CMOS cameras also had pretty low resolution because all that logic had to be also mixed in with the different pixels. But more and more people managed to also get high resolution CMOS cameras, as you see here. So by 2015, you already had in mobile phones a lot of really good resolution cameras, CMOS cameras, that is. Here a comparison. So if you have CCD cameras versus CMOS cameras, CCD cameras by now are more for niches. If you really want to have the highest quality of imagery, it may still be a good idea to look at CCD cameras. Unfortunately, CCD cameras use specific technology. So if you have a production line for CCD cameras, you cannot easily turn that into a production line for CPU processes. On the other hand, for CMOS, it's not for niches, that's consumer products, mobile phones, what have you, all CMOS cameras. It's standard IC technology. The same production environment you use for the production of CPUs or memories can be used for the production of CMOS cameras as well. CCD cameras needing all those special environments make them costly in terms of their production. In comparison, CMOS cameras are cheap. CCDs also require more energy to be operated. In comparison, CMOS cameras are low powered. As we mentioned, CCDs have a better fill rate. The percentage of the chip that you can make light sensitive is higher. So CMOS cameras are less sensitive, although special techniques like adding the pixels with micro lenses and stuff like that helps to reduce that disadvantage of CMOS compared to CCD. CMOS cameras have much less problem with so-called blooming than CCD cameras. And blooming means that if you have very bright light that sends so many photons to your sensor, at some point the bucket collecting these photons in the sensor would overflow. And then the question is, what happens? In a CMOS, not much. Unfortunately, in a CCD camera, that pixel will start to influence its neighbors. The neighbors along the charge-coupled device, the charge-coupled register, generating overflow in the neighbors, that they may even overflow in their neighbors. So what you sometimes see is that if you have a very bright spot in a CCD camera, you get an entire line of overexposed illumination. So in the CMOS camera you have much less of that. You can even control the illumination levels, the sensitivity per pixel with a per pixel amplification. You have the logic right there next to the chip. A CCD lives by the idea of shifting out information, so it's a slow process. It's a very sequential process. CMOS, behaving more like a memory, there you can also provide really partial readouts. So you could build CMOS chips in which you can read out parts much faster. Additional advantage of CMOS, the smart pixels that we mentioned, so we can mix in logic, local processing, with the different pixels, and also the on-chip integration of the camera, memory, processing. Here an example, with a CCD camera, we have the same kind of amplification per pixel. It's an image taken in a tunnel, and you see that the outside, where you have daylight, is very, very bright, too bright actually. Whereas with a CMOS camera, you can locally adapt the levels of amplification. So here you can have a sharp image outside and inside the tunnel all at once. In fact, 2006 was the year when for the first time there were more CMOS cameras put into the market than CCD cameras. And ever since, the balance has been tipped more and more in favor of CMOS cameras. So by now, CCD is becoming almost like an extinct technology. In fact, in 2015, the champion of CCD camera production, Sony, were also at a point of stopping all CCD chip production.